This is section 2.7, Parent Functions and Transformations. Our objective is I can identify a function given a graph, and I can describe and graph translations, reflections, and dilations. A family of graphs is a group of graphs that display one or more similar characteristics. The parent graph, which is the graph of the parent function, is the simplest of the graphs in a family. This is the graph that is transformed to create other members in a family of graphs. In example 1, we're going to identify the type of function represented by each graph. On A, we can see that it's a parabola. So based off of the 4 types of parent functions, we know that it's going to be a quadratic function. In example B, it's a line. So if we look at the 4 parent functions, we know that it's going to be an identity function. In example 3, we just have a horizontal line. So we know that the parent function of this graph is going to be the constant function. And in example D, we have a V shape, which we know goes with our absolute value function. Transformations of a parent graph may appear in a different location, flip over an axis, or appear to have stretched or compressed. The transformed graph may resemble the parent graph, or it may not. A translation moves a figure up, down, left, or right. When a constant k is added to or subtracted from a parent function, the result, f of x plus or minus k, is a translation of the graph up or down. When a constant h is added to or subtracted from x before evaluating a parent function, the result f of x plus or minus h is a translation left or right. In example 2, we're describing and graphing translations. In A, it says to describe the translation in y is equal to the absolute value of x plus 2, and then to graph the function on the same graph as the parent function. So if you go ahead and look at the graphs that we have, this is actually the parent function of the absolute value function. So before we go ahead and do this, we're going to create a t-chart. So we have x, y, and we've done these before, so we know that we can choose a few different values. I'm just going to start out with -1, 0, and 1, and see if that gives us enough information. Now remember, if it doesn't create a v, we're going to have to use some other values. So using -1, we have the absolute value of -1 plus 2. The absolute value of -1 is positive 1, so we end up with 1 plus 2, which is 3. The absolute value of 0 plus 2 is equal to 0 plus 2, which is 2. And the absolute value of 1 plus 2 is equal to 1 plus 2, which is 3. So let's go ahead and graph what we have come up with from our t-chart and see what that looks like. So we're going to have points at -1, 3, 0, 2, and 1, 3. And if we go ahead and connect all of these dots, we see that we do have a V shape already, which means that we do have an absolute value function. We don't need to worry about plugging in any more x values. And we need to describe the translation that's happened. So if we take a look at this, we see that this point moved up 2 spots. This point moved up 2 spots, and this point moved up 2 spots, which means that our graph moved up 2 units. In example B, we're doing the same type of thing. So let's go ahead and start off with our t-chart. Again, I'm just going to use -1, 0, and 1. and plug those values in. So we're going to have -1 plus 2 in absolute value signs. So -1 plus 2 gives me +1, and the absolute value of +1 is just 1. Then we have the absolute value of 0 plus 2. 0 plus 2 is equal to 2, and the absolute value of 2 is 2. When we plug in 1, we have the absolute value of 1 plus 2, which is equal to 3. So we have the absolute value of 3, which is just 3. If we go ahead and graph these points, we have -1 up to 1. We have 0 up to 2. And we have 1 up to 3. Now here's an example that doesn't create a V yet, so we know we're going to have to plug in some other points. If we take a look at this, we know that if we plug in value 2, we're probably going to get a point up here. Value 3, we're probably going to get a point up here. So I'm going to plug in some values over here and see if that helps us out. If I go ahead and plug in -2, I'm going to have the absolute value of -2 plus 2, and -2 plus 2 is 0. And the absolute value of 0 is 0. So if I graph that point, I'm going to have a point right here. Still, that doesn't help me. So I'm going to go ahead and try -3. If I plug in -3, I'm going to have the absolute value of -3 plus 2, which is going to give me the absolute value of -1, which is 1. So if I graph that point, I'm going to have -3 up to 1, and then I can see that this is going to create my absolute value shape, my V shape. So I can go ahead and graph, and then I can go ahead and say what's happened with this graph. Now if you look, this graph hasn't moved up or down, it's just moved to the left. And from this point, we move 2 units to the left. From this point, we're also moving 2 units to the left. So we can say that the graph shifted 2 units to the left when we describe the translation that's occurred. A reflection flips a figure over a line called a line of reflection. We can think about a mirror because it's really just going to mirror what the graph already is. When a parent function is multiplied by -1, the result, -f of x, is a reflection of the graph in the x-axis. When the independent variable is multiplied by -1, the result f of -x is a reflection of the graph in the y-axis. So we can have 2 types of reflections. In example 3, we're describing the reflection y equals -x squared. And then we're going to graph. I'm going to go ahead and graph this dude first using my t-chart. So if I have x, y, I can plug in several different values. I'm just going to start off with -1, 0, and 1 and see if that gives me enough information. When you plug these in, don't forget that you need to put parentheses around whatever value you're plugging in for x. So for these values, we're going to have negatives on the outside, and then we're just going to have -1, 0, 1 on the inside, and then a squared on the outside. Now, what this means, we have to follow our order of operations. So we're going to do the squaring part first, and then worry about that negative that's on the outside. So -1 squared is going to give me +1, but then I still have that negative that's on the outside of my parentheses, and so my answer is going to be -1. 0 squared is just going to equal 0, and I have a negative on the outside, which would be -0, but there's no such thing as -0, so we're just going to say 0. 1 squared is going to be +1, but then again, we have a negative we have to deal with on the outside, so we're going to get -1 as our answer. So if we go ahead and go to graph these, we have -1, -1. We have 0, 0. And we have 1, -1. So we can already tell that this is going to give us the shape of a parabola, so we don't need to worry about any other points. We can just go ahead and graph what we have. And And we can see that there has been a reflection, and the reflection has occurred over the x-axis here. So when we describe what's happened here, we're going to say the graph reflects over the x-axis. The last example we're going to look at is a dilation. A dilation shrinks or enlarges a figure proportionally. When the variable in a linear parent function is multiplied by a non-zero number, the slope of the graph changes. When a nonlinear parent function is multiplied by a non-zero number, the function is stretched or compressed vertically. Coefficients greater than 1 cause the graph to be stretched vertically, and coefficients between 0 and 1 cause the graph to become compressed vertically. In example 4, it says to describe the dilation of y equals 4x and then graph the function with the parent graph. So the parent graph is already given to us. Again, we're going to set up a t-chart for this. So if I set up a t-chart, x, y, I'm just going to use a few different numbers again and see if it gives me enough information. -1, 0, and 1. If I plug in -1, I'm going to have 4 times -1, which is -4. Plugging in 0, I'm going to have 4 times 0, which is 0. And plugging in 1, I'm going to have 4 times 1, which is 4. I'm going to go ahead and draw some units on our graph. And what we notice about the parent function is that there's always going to be points at 1, 1, 0, 0, -1, 1. So if we go to graph our new function, we have -1 down to -4, which is going to be about right here. We have 0, 0, and we have 1, 4. When we graph our line, we can see that the slope has gotten steeper, and that's what we can write for being able to describe the dilation. Now, a lot of my students, when they took the quiz on this, they didn't understand. They thought they needed to say that a dilation occurred. I'm not looking for you to tell me that a dilation or a translation has occurred, or a reflection. I'm just looking for you to tell me exactly what's happened with the graph. So in this case, you wouldn't need to tell me a dilation has occurred. All you would need to tell me is that the graph has gotten steeper. Also, with translations, you wouldn't have to say that a translation has occurred. You'll just need to tell me if it moves right, left, up, or down, and how many units.